This video is for topic 5.1, so chapter 5 or unit 5. The main thrust of this section is the mean value theorem, abbreviated MVT. So it's another one of our big theorems. I think your second one. We did intermediate value theorem and now we're doing mean value theorem. So it says, before we introduce the main topic, the mean value theorem, let's start with a special case, which is called Rolle's theorem, which honestly does not come up that often, but it starts with an activity. So I suggest that you pause the video and try this activity. And then we're going to assume you pause the video. Yours might look different. So it says place 2 points anywhere on the coordinate plane. I'm trying to place them by a coordinate point that have the same y value. I did not do that. Let me do that. Connect the 2 points with a continuous function that is also differentiable. So no corners, no cusps, no nothing. Doesn't matter what it looks like. I chose to do that. So it says, conclusion, there must be at least one point on your function where you can draw a tangent line that is horizontal, where the slope is 0, or where the slope of the tangent line is 0, or where the derivative is 0. So on the graph that I drew, there's actually 3 of them, but on whatever graph you drew, there should be at least one of them. This activity basic models the Rolle's theorem. So it says if the function is continuous and you have 2 of the same y values, then you must somewhere have a spot where you can draw a horizontal tangent. This is another one that I drew earlier, and it had 2. And then this summarizes Rolle's theorem right here. So if you're using Rolle's, you first have to say you're continuous. This is on a closed interval. Remember, these are x values. And differentiable on the open interval. So differentiable everywhere except the endpoints. So if f of a equals f of b, so this is the same y values that we did. There is at least one number c between a and b such that the derivative or the slope of the tangent line is 0. So if this were my point A, and this was my point B, this would be f of b, this would be f of a. It says there exists a c between a and b where the derivative will be 0. So in my case, there's 3 c's between a and b. Okay, turn the page. Illustrating Rolle's theorem. So again, we're looking for that horizontal tangent line or where the derivative is 0. So determine if Rolle's theorem applies to this function. Oops, where is it? There it is. On the interval -2 to 2, state thoroughly the reasons why or why not the theorem applies. If the theorem does apply, find the value of c that is guaranteed by your theorem, and then check it in your graphing calculator. So f of x is a polynomial, and so that implies it is continuous on this interval. It's actually continuous everywhere, and it's differentiable because polynomials are always differentiable. D-I-F-F-E-R-E-N-T-I-A-B-L-E. Okay, on the open interval, which are the requirements for Rolle's theorem. So you need to start with the requirements. I'm going to zoom in a little. So now I need to find what they call in the theorem f of a and f of b, which in our case will be f of -2 and f of +2. So that's at the 2 endpoints. So -2 would be -2 to the 4th minus 2, -2 squared, which is 16 minus 8, which is 8. F of +2 would be 2 to the 4th minus 2, 2 squared. which again is 16 minus 8, which equals 8. So this is f of negative 2 equals f of 2, and they both equal 8. This is the two y values, or f of a equals f of b. So then I've met the requirements for roles, so that means somewhere between negative 2 and 2, there should be a number where the derivative is 0. So I have shown that it applies because all these things are true. Now we're going to find c. So to find c, we need f prime of x, which will be 4x to the third minus 4x. Set that equal to 0. And solve. That is factorable. Factor out a 4x, and you have x squared minus 1. Factor again. X squared minus 1 factors into x plus 1, x minus 1. So at x equals 0, x equals plus or minus 1, the derivative is 0. So there does exist a c, and all three of them are between negative 2 and 2. And at those x values, the derivative is 0. If you went ahead and graphed this in your calculator, kind of looks like the one I put on the last page. So points there. Let's see how well I can do this. And so at 0, you have a horizontal tangent, at negative 1, and at positive 1. All right, mean value theorem. You will need a ruler for this. So here's my ruler. Okay, it says in the figure to the right, label the indicated ordered pairs. Label the line segment whose length is f of b. Oh, well, first we need to label the ordered pairs. So if this is A, this point right here, the x is A, and the y is what I get when I plug A into the function. So the y is f of A. This x value is b, and the y is what I get when I plug b into the function, or f of b. So function notation. So that's number 1. Number 2, it says label the segment whose length is b minus a. Label the segment, whose length is f of b minus f of a. So here's f of b, here's f of a. The segment whose length is f of b minus f of a, I'm going to kind of make a box here. Going from there to there. Okay, so this right here, the top of this is at f of b, and the bottom is over here at f of a. So this segment right here is what they're asking for in number 2. So this is number 2. The length of that is f of b minus f of a. This segment right here. Label the segment whose length is b minus a. So these are x values, so this should be a horizontal. That's this distance right here. So this is number 3, b minus a. The quotient, f of b minus f of a over b minus a, is that should look familiar, that's algebra 1 slope. Slope of the segment joining the 2 points, a, f of a, and b, f of b. So this is what we call the secant line. Algebra 1 slope finds the slope between 2 points, and so it's the secant line. I'm going to do a dashed line between here. So this is the slope that they're asking for from this point to this point. And so f of b minus f of a, or f of b, minus f of a is the same as y2 minus y1. over x2 minus x1. So we call that the slope of the secant line. Now, derivative gives the slope of the tangent line. So it gives the slope of the line tangent to the curve of f of x at the point C, f of C. So slope of the tangent line. We don't have a point C on our graph, but we could put it, and then that would be the slope of the tangent line. Okay, you're probably wondering, where is this going? So it says, on the graph above, locate the value C that is guaranteed by the mean value theorem and draw a line tangent to the curve at x equals C. So I'm going to put C right there in between A and B. There's the slope of my tangent line. Right there. Right there. Scroll back down here. Okay, now this is the big thing of the mean value theorem. The two lines drawn on the graph of f of x are parallel. And then remind yourself, parallel lines have the same slope. So I'm just going to go up here and kind of show you what mean value says. Mean value theorem says if you have a function and it's continuous and differentiable, then somewhere, in this case, it was at point C, there exists a point where the slope of the secant line, or the algebra 1 slope, equals the slope of the tangent line, or the derivative. So it's where derivative, the slope of this line, equals algebra 1 slope, the slope of the secant line. So it says, thus, the conclusion of the mean value theorem can be restated as follows. There will be two parallel lines, one through the points, this is the algebra 1 slope, A, f of A, and B, f of B, and the other tangent to the curve, so that's your tangent line, tangent to the curve at the point C, f of C, parallel lines, which mean they have the same slope. So these are both lines, and if they have the same slope, then they are equal. So what we have going on here is algebra 1 slope equal to derivative. And I think on the next page we have the formal definition. Yes. So again, like all the theorems, you can abbreviate this one MVT. You will have to show continuous on the closed interval and differentiable on the open interval. So we're just leaving off the endpoints. There exists a C in this interval such that this is derivative is equal to algebra 1 slope. Okay, let me do example 2. This lesson is definitely going to have to be 2 videos. So it says, determine if the mean value theorem applies. They give me a function, they give me an interval, so I'm thinking I have to show it's continuous. State thoroughly the reasons why or why not the theorem applies. So the reasons it wouldn't apply is if it's not continuous or not differentiable. If the theorem does apply, then find C guaranteed by the theorem. Visually, what is the mean value theorem trying to find? Draw it in. So let's draw it in first before we solve this problem. Okay, I'm looking at x value 1 and 5. So here's 1. So I'm going to put a point at x equals 1 and on the curve, and a point at x equals 5 and on the curve. Draw a secant line between those points. So that would be that. Now what mean value theorem says is the slope of the secant line will be the same slope as the tangent line. So take your ruler and slide it, keeping that same slope until you're tangent to the curve. And it says there exists a point, there it is, right there, C, where the slope of the tangent line is the same as the slope of the secant. So if our drawing's decent, our C should end up to be right about there. Okay, so we have to talk about continuity and differentiability. So this function is continuous on the interval 1, 5. Notice it's not continuous when x equals 0, but it is continuous on this interval from 1 to 5. So f of x is continuous on the closed interval 1 to 5. And it's also differentiable. It looks polynomial-ish once you get beyond the x equals 0. So it is also f of x is differentiable. On open interval, 1 to 5. Okay, so those are basically the requirements of mean value theorem, continuous and differentiable. So it does apply, so I've kind of answered the first question up here. So then it goes on to say, well, find that C value. So to find the C value, I need to do algebra 1 slope and derivative, set them equal to each other, and find that x value is what we're really going to find. So let's do derivative first. So f prime of x would be, you could write this function as 3 minus 5 times x to the negative 1. You can't see that. There we go. And then you can just use power rule on this. So derivative would be 0 plus 5x to the negative 2, or 5 over x squared. Okay, so this is derivative. Now let's find algebra 1 slope, which is going to be f of 5 minus f of 1 all over 5 minus 1. F of 5 will be 3 over 5 minus, or 5 divided by 5. F of 1 will be 3 minus 5 divided by 1 all over 4. Ooh, kind of running out of room here. I'm going to go down. This is 3 minus 1. This is 3 minus 5. So minus 3 plus 5 if you distribute that negative. And so you get 4 over 4, or 1. Negative 3 and positive 3 are 0. Okay, so this is algebra 1 slope. This is derivative right there. So I just want to set those equal and solve for x. So I would get x squared equals 5. X equals plus or minus square root of 5. I'm going to ignore negative square root of 5 because it's not, negative square root of 5 is not on the interval 1 to 5. So we're going to ignore the negative answer. So therefore, the value of C guaranteed by mean value theorem is square root of 5. Okay, if you put square root of 5 in your calculator, you get approximately 2.2360, blah, blah, blah. And if you go back to what we sketched here, we said our C was a little more than 2. So our sketch was verified down here. Okay, I think I'm going to put the next 3 examples in the next video.